Welcome to another deep dive. You, the learner, have presented us with a truly fascinating challenge this time, and it all starts with this massive stack of information, the detailed curriculum for the Pre-C course for graduate marine engineers at the Great Eastern Institute of Maritime Studies.
Yeah, it's quite a bit.
It really is, and this deep dive is going to be your rapid immersion course in all the core knowledge these aspiring engineers gain during their intense 8 months of onshore training.
8 months. That's a pretty serious commitment right there.
No kidding. Our mission is to navigate this mountain of material and surface with you, bringing back the most insightful and captivating aspects to give you a real feel for what it takes to operate and maintain the complex machinery that powers global shipping.
That's it, the stuff that keeps the world turning, really.
Literally, we're going to be drawing directions from their syllabus, covering everything from the basic physics of, well, how our ship floats, to the inner workings of these massive diesel engines, the intricacies of onboard electrical systems, the critical importance of safety and environmental regulations, and even, get this, the nuances of leadership on the high seas.
Sounds like a wild ride.
Buckle up, let's jump right in.
Let's do it.
All right, first stop, naval architecture, ship construction, and stability. And it all begins with, you guessed it, some fundamental terms.
The building blocks, as it were.
Exactly. Displacement, wetted surface, coefficients like block, midsection, prismatic, and water plane area coefficient. Now, I know these might sound like dry technicalities, but trust me, they're absolutely crucial.
Oh, they're the foundation of everything. You can't even begin to talk about a ship without understanding these terms.
So why are they so important?
Well, think about it like this. These terms are the language we use to describe a ship's form, how it interacts with the water. Take displacement, for instance. This is all about how much water the ship pushes aside, which, amazingly, is exactly equal to the ship's own weight.
A multi-thousand-ton vessel held afloat by that one principle.
It's mind-blowing, isn't it? A principle discovered by Archimedes centuries ago, still relevant today. And then there's wetted surface area, the part of the hull in contact with the water which directly impacts drag. The less wetted surface, the less resistance, the faster the ship can go.
So it's all about minimizing that contact, right?
Exactly. And then we have the coefficients. These are like secret formulas, in a way, that allow naval architects to fine-tune the hull shape for optimal performance. Do you want to maximize cargo space, achieve higher speeds? The coefficients help you find the sweet spot.
So it's like the perfect balance between form and function, right?
Precisely. Each ship has a specific purpose, and these coefficients help us achieve that purpose in the most efficient way possible.
Fascinating. And then we move on to stability, another absolutely critical aspect. Buoyancy, center of gravity, the metacenter, and the inclining experiment. These terms may sound familiar, but understanding them in the context of a massive ship at sea is a whole other level.
It's all about equilibrium, really, the balance of forces that keeps a ship upright and prevents it from capsizing.
So break it down for us. Buoyancy, we all kind of know what that is, right?
Yeah, it's that upward force that keeps things afloat. In the case of a ship, it's the force exerted by the water that's displaced by the hull. Now, every ship has a center of gravity, the point where all its weight effectively acts downwards. For a ship to be stable, the center of buoyancy, that's the center of the underwater volume, needs to be in the right relationship with the center of gravity.
Okay, I'm starting to see how this all fits together. So what about the metacenter?
Think of the metacenter as a sort of imaginary pivot point. If, when the ship tilts slightly, the metacenter ends up above the center of gravity, the ship will right itself. It's like a self-righting mechanism.
That makes sense. And the inclining experiment, what is that all about?
That's a real-world test where weights are strategically moved onboard to precisely determine the ship's center of gravity. This information is crucial for ensuring stability calculations are accurate. It's like double-checking the math, making sure the ship is as stable as it needs to be.
Right, because without stability, well, the ocean is a pretty unforgiving place.
It doesn't take much for a ship to lose its balance and face serious trouble.
So we've talked about a ship's form, its stability. Now let's get into the forces it has to endure at sea. The syllabus mentions hogging, sagging, panting, and pounding. What are these?
Well, these are the stresses that a ship's structure has to withstand, the constant battle against the elements, if you will. Hogging and sagging refer to the bending of the entire hull along its length. Sagging happens when the weight in the middle is greater than at the ends, like a beam supported at both ends with a heavy load in the center. Hogging is the opposite, where the ends are heavier.
So imagine a ship loaded with cargo in the middle. That would cause sagging, right?
Exactly, and if the cargo is concentrated at the ends, you get hogging. Now, panting and pounding are more localized impacts. Panting is the flexing of the hull plating, especially at the bow and stern, in response to water pressure. Imagine waves constantly hitting the hull, causing it to flex inwards and outwards. That's panting.
Sounds pretty intense.
It can be, especially in rough seas. And then there's pounding, which is the slamming impact when the bow of the ship rises out of the water and then crashes back down.
Ouch. That sounds like it could do some serious damage.
It absolutely can. That's why understanding these stresses is vital for designing a hull with the right strength and structural integrity to withstand these relentless forces.
So it's all about anticipating these forces and building a studding that can handle them.
Exactly. You have to over-engineer things to a certain extent, factor in a safety margin because the sea is unpredictable, and you never know what kind of punishment a ship might have to endure.
Makes sense. Okay, so we've covered the ship's form, its stability, the stresses it faces. Now, let's talk about how these massive structures actually move through the water, resistance and propulsion.
The art of moving a floating city, so to speak.
Exactly. And we encounter terms like skin frictional resistance, residual resistance, different types of propellers, fixed pitch, controllable pitch, even ducted propellers, and then there are those fascinating propeller calculations involving pitch, slip, and wake. Break it down to us. How do engineers tackle the challenge of moving these behemoths sufficiently through water?
It's all about understanding and overcoming resistance. Think of resistance as anything that tries to slow the ship down. Skin frictional resistance is like the friction of the water molecules rubbing against the hull. The smoother the hull, the less friction, the better.
So it's like minimizing the pumps on a surface, right?
Yeah, exactly. And then there's residual resistance, which accounts for other factors like wave-making drag. A ship moving through water creates waves, and those waves actually push back on the ship, creating resistance.
Wow, that's amazing. So how do we overcome all this resistance? Enter the propeller, right?
The propeller is the hero of the story. It's what converts the engine's power into thrust, pushing the ship forward. Now, there are different types of propellers, each with its advantages and disadvantages. Fixed-pitch propellers are simple and efficient for a specific operating speed.
So if you know the ship will mostly be cruising at a certain speed, a fixed pitch propeller makes sense.
Exactly. But if you need more flexibility, say for maneuvering in tight spaces or operating in different sea conditions, you might opt for a controllable pitch propeller. These allow you to change the angle of the blades, giving you much more control over speed and direction without altering engine RPM.
So it's like having gears on a car, essentially.
Yeah, a good analogy. And then there are ducted propellers, which have a shroud around them. This can sometimes improve efficiency by directing the water flow more effectively.
So it's all about optimizing that flow, getting the most thrust out of the propeller.
Exactly. And then we have those propeller calculations, pitch, slip, and wake. Pitch is the theoretical distance a propeller would move forward in one rotation if it were moving through a solid. Slip is the difference between that theoretical distance and the actual distance it moves through water.
So there's always some loss, some slipping, right?
There is, and minimizing that slip while maximizing thrust is a constant challenge for engineers. And then wake is the disturbed flow of water behind the ship, which can also affect propeller performance.
So it's a complex interplay of forces, and propeller design is all about finding the optimal balance for a particular ship and its intended use.
Absolutely. It's a fascinating area of engineering, and it's constantly evolving as we strive for greater efficiency and performance.
So we've talked about a ship's form, its stability, the stresses it faces, and how it moves through the water. Now let's dive into the language of ship construction. The syllabus introduces a whole lexicon of maritime terms: length between perpendiculars, breadth overall, molded depth, draft, freeboard, camber, and more. Why is this specific vocabulary so important?
Well, this standardized terminology is the bedrock of communication within the entire maritime industry. It ensures everyone, from naval architects to shipbuilders to port authorities, is speaking the same language.
Like a universal code for all things maritime.
Precisely. For instance, length between perpendiculars and breadth overall give you precise measurements of the hull. Molded depth tells you the vertical height of the hull. Draft is how deep the ship sits in the water, critical for navigating channels and harbors.
So if you're approaching a port with a shallow entrance, you need to know your draft to make sure you don't run aground.
Absolutely. And then there's freeboard, the distance between the waterline and the main deck. This is a crucial safety margin. The higher the freeboard, the less likely the ship is to be swamped by waves. Cambered refers to the curvature of the deck, which helps with drainage.
So it's not just about aesthetics, it's about functionality.
Exactly. Every detail has a purpose, and this abridized vocabulary ensures everyone understands those purposes and can communicate effectively.
Makes perfect sense. The syllabus then discusses hull construction, the arrangement of spaces accommodation, cargo, machinery, watertight doors and hatches, regulations surrounding the carriage of dangerous goods. It's like designing a floating city, isn't it?
It is a self-contained world with its own rules and regulations. The arrangement of internal spaces is meticulously planned to optimize workflow, ensure crew comfort, and also segregate potentially hazardous areas.
So you don't want the engine room right next to the crew quarters.
Exactly. And watertight doors and hatches are fundamental to the ship's ability to withstand flooding. They can isolate breaches and prevent the entire vessel from being compromised. And the regulations for carrying dangerous goods are incredibly strict. It's all about safety, mitigating risks, and protecting both the crew and the environment.
Speaking of safety, the syllabus mentions load lines and draft marks, specifically the deck line and the plimsoll line. What's the story behind these markings?
The plimsoll line, it's a simple mark with a powerful history. Back in the 19th century, a guy named Samuel Plimsoll, a member of parliament, campaigned tirelessly to end the practice of overloading ships.
Which was, sadly, a common practice back then.
It was, and it led to countless lives lost. Plimsoll fought to establish a mandatory load line, a mark that indicated the maximum safe draft for a ship. Today, the plimsoll line, or load line, is a standard feature on all cargo ships, and it's a testament to the importance of safety regulations in the maritime world.
A powerful reminder that these regulations are often born out of tragedy and a commitment to preventing future disasters.
Exactly. We learn from the past and strive to make shipping safer for everyone.
The syllabus then briefly describes different types of ships: general cargo, tankers, bulk carriers, container ships, ro-ro, and passenger ships, highlighting their specific design considerations. It's amazing how specialized these vessels have become.
It's a reflection of the globalized world we live in, where goods and people are constantly on the move. Each type of ship is tailored to its specific trade, optimized for efficiency and functionality.
So give us some examples.
Well, take a container ship, for instance. These are designed for speed and efficiency, carrying standardized containers across vast oceans. They're sleek, they have powerful engines, and their internal layout is all about maximizing container capacity.
And then you have bulk carriers, right?
Bulk carriers are the workhorses of the sea, transporting vast quantities of raw materials like iron ore, coal, or grain. They're massive, they have wide beam hulls, and their cargo holds are designed for easy loading and unloading.
And tankers, they're a whole other beast.
Tankers are like floating pipelines transporting oil, chemicals, or liquefied gas. They have sophisticated systems for safely loading, transporting, and unloading these potentially hazardous liquids. And then there are ro-ro ships, which are essentially floating parking garages for vehicles. Each type of ship has unique structural requirements, stability considerations, and machinery arrangement optimized for its particular purpose.
It's like a whole ecosystem of specialized vessels, each playing a crucial role in global trade.
Exactly. And understanding these different ship types is essential for marine engineers, as they may end up working on any of them.
Makes sense. Finally, in this section, we touch upon classification societies and surveys. What role do they play in maintaining standards across the global fleet?
Classification societies are like the guardians of maritime safety. They're independent, non-governmental organizations that establish and maintain technical standards for the design, construction, and operation of ships. They develop rules and regulations covering everything from hull strength to machinery and safety systems. And throughout a ship's life, they conduct regular surveys to ensure the vessel continues to comply with these standards.
So they're like the independent auditors, making sure everyone is playing by the rules.
Exactly. It's a crucial system of checks and balances that helps ensure the safety of ships, their crews, and the marine environment.
All right, we've covered a lot of ground here, but I think we've got a pretty good grasp of the fundamentals of naval architecture and ship construction. Now let's venture below deck and explore the heart of the ship: marine diesel engines and engine room watchkeeping.
Time to get our hands dirty.
Let's do it. This section kicks off with the core: basic construction and operation principles of marine diesel engines. We encounter terms like two-stroke and four-stroke cycles, and we delve into the key components like the crankshaft, camshaft, pistons, cylinder liners, and cylinder heads. These are the building blocks of the engines that power most ships.
And they're marvels of engineering, really. Think about it. Massive, powerful machines that can run for days, weeks, even months on end, reliably propelling a ship across vast oceans.
So what's the difference between a two-stroke and a four-stroke engine?
It's all about the cycle of events that happens inside the cylinder. In a four-stroke engine, you have four distinct strokes: intake, compression, power, and exhaust. In a two-stroke engine, you cram all those events into just two strokes. This means a two-stroke engine can produce more power for a given size, but it's also generally less efficient and produces more emissions.
So it's a trade-off between power and efficiency. And what about all those components you mentioned?
Each one plays a crucial role in the engine's operation. The crankshaft converts the up and down motion of the pistons into rotary motion, which ultimately turns the propeller. The camshaft controls the timing of the valves, allowing air and fuel into the cylinders and exhaust gases out. The pistons compress the air and fuel mixture, which ignites to produce the power stroke. The cylinder liners form the walls of the combustion chamber, and the cylinder heads seal the top of the chamber and house the valves.
It's amazing how all these work together in perfect synchrony. The syllabus then delves into scavenging and supercharging, two processes that help these massive engines breathe efficiently. How do they work?
Well, scavenging is essentially the process of flushing out the exhaust gases from the cylinders after combustion and replacing them with fresh air ready for the next cycle. This can be done in a few ways, depending on the engine design.
So it's like clearing the lungs for the next breath.
Exactly. And then there's supercharging, which is all about forcing more air into the cylinders than would naturally be drawn in. This is often achieved with a turbocharger, a device that's driven by the exhaust gases themselves.
So you're using the waste energy from the exhaust to power the turbocharger, which then forces more air into the engine.
Exactly. More air means more fuel can be burned, resulting in a significant increase in power without a proportional increase in engine size. It's a clever way to boost efficiency and performance.
Next up, we have combustion and fuel injection systems. Getting the fuel to burn efficiently and cleanly in these enormous cylinders must be a significant engineering challenge.
It is, and fuel injection systems play a critical role. They deliver the precise amount of fuel at the optimal pressure and at exactly the right moment into the combustion chamber. This ensures efficient and complete combustion, which maximizes power output and minimizes emissions.
So it's like fine-tuning the fuel delivery for optimal performance.
Exactly. Modern fuel injection systems are incredibly sophisticated, with electronic controls and sensors that constantly monitor and adjust the fuel delivery process.
And then we have cooling and lubrication systems, the unsung heroes that keep everything running smoothly and prevent catastrophic failures.
These systems are absolutely vital. Imagine the intense heat generated inside a massive diesel engine. Without a cooling system, the engine components would quickly overheat and fail. The lubrication system is equally important. It reduces friction between all the moving parts, minimizing wear and tear and extending the engine's lifespan.
So it's like the oil in your car, only on a much larger scale.
Exactly. The lubrication system ensures that all those moving parts are constantly bathed in oil, reducing friction and heat buildup.
The syllabus also covers starting and reversing mechanisms. How do you get such a massive engine turning, and how do you reverse the thrust to maneuver a ship?
Starting these large engines often involves using compressed air, which is forced into the cylinders to turn the crankshaft. Once the engine is turning over, the fuel injection system kicks in and the combustion process begins.
So it's like a giant air starter. And how about reversing?
Reversing can be achieved in a few ways. Some engines have mechanical linkages that physically change the timing of the valves or camshaft to reverse the direction of rotation. However, many modern ships, especially those with controllable pitch propellers, simply reverse the pitch of the propeller blades to change the direction of thrust.
So the engine keeps running in the same direction, but the propeller pushes the water in the opposite direction, causing the ship to move backwards.
Exactly. It's a clever way to achieve reverse thrust without having to physically reverse the engine itself.
Maintenance, of course, is a huge part of keeping these engines operational. The syllabus highlights planned schedules, cylinder head routines, and decarbonization. It's all about preventing problems before they occur, right?
Absolutely. Proactive maintenance is the key to ensuring the reliability and longevity of these complex machines. Planned maintenance schedules dictate regular inspections and servicing of various components based on running hours or other factors.
So it's like taking your car in for regular oil changes and tune-ups.
Exactly. And cylinder head routines involve checking and servicing the critical valves and seals in the cylinder head, which are exposed to extreme temperatures and pressures. Decarbonization is the process of removing hard carbon deposits that accumulate in the combustion chamber over time, which can impede efficiency and even cause damage if left unchecked.
Sounds like a messy job.
It can be, but it's essential for keeping the engine running smoothly.
The syllabus also addresses potential hazards like scavenge fires, starting air explosions, and crankcase explosions. These sound like pretty serious risks. What are the safety measures in place to prevent these incidents?
These are indeed significant hazards associated with large diesel engines. Scavenge fires can occur in the exhaust gas passages, often due to a buildup of unburned fuel or oil. Starting air explosions, thankfully rare, the modern safety systems, can occur if fuel enters the compressed air system used for starting. And crankcase explosions caused by the ignition of oil mist in the crankcase can be extremely dangerous.
So it's a volatile environment, and safety is paramount.
Absolutely. To mitigate these risks, engines have various safety systems in place, like governors to regulate engine speed, overspeed trips that automatically shut down the engine if it exceeds safe limits, and oil mist detectors that provide early warning of a potential crankcase explosion.
So it's a multi-layered approach to safety, with systems designed to prevent these hazardous situations from developing in the first place, and systems in place to mitigate the damage if they do occur.
Exactly. It's all about minimizing risk and ensuring the safety of the crew and the vessel.
Emission control is also a major focus these days, with regulations getting increasingly stringent. The syllabus mentions SOx and NOx reduction methods. How are these harmful emissions being tackled?
Reducing emissions from ships is a global priority, and there's a lot of research and development going into finding effective solutions. Sulfur oxides, SOx, are primarily controlled by using fuels with very low sulfur content or by installing exhaust gas cleaning systems known as scrubbers.
So it's either cleaner fuel or cleaning the exhaust gases.
Exactly. And nitrogen oxides are tackled through engine design modifications and technologies like selective catalytic reduction, SCR systems, which treat the exhaust gases to reduce NOx emissions.
It sounds like a constant battle to stay ahead of the regulations and find ever more effective ways to reduce the environmental impact of shipping.
It is, but it's a battle we have to win. The health of our planet depends on it.
The syllabus concludes this section by briefly introducing some recent developments like camshaftless engines, such as the Sulzer RT Flex and B&W ME engines. What's so special about these engines?
These are game changers in the world of marine diesel engines. They represent a radical departure from traditional engine design, moving away from mechanically driven camshafts to electronically controlled systems. This allows for much greater flexibility in optimizing the combustion process, potentially leading to improved fuel efficiency and reduced emissions.
So it's like taking the mechanics out of the equation and replacing them with sophisticated electronics.
Exactly. It's a major technological leap forward, and it's likely to have a significant impact on the future of shipping.
Okay, we've covered a lot of ground here on marine diesel engines. Now let's shift our focus to the human element, engine room watchkeeping. It's not just about understanding the machinery, it's about managing it effectively and safely.
It's about teamwork, vigilance, and a deep understanding of the systems under your care.
The syllabus outlines the principles of watchkeeping, the duties during a watch, safety procedures, and engine room resource management, covering manpower, spares, communication, and teamwork. It's a holistic approach to managing this complex environment.
Watchkeeping is the cornerstone of safe and efficient engine room operations. It involves continuous monitoring of the machinery, regular checks and inspections, and meticulous record-keeping in the engine room logbook.
So it's not just about sitting in a chair and staring at gauges.
Not at all. It's about actively engaging with the machinery, listening for any unusual sounds, checking temperatures and pressures, and being constantly aware of the overall health of the systems.
And engine room resource management, what does that entail?
It's about effectively utilizing all available resources the engineers on watch, the spare parts inventory, the tools and equipment, and fostering clear communication and strong teamwork to prevent accidents and ensure smooth operations.
So it's about leadership, decision-making, and communication.
Absolutely. The engine room is a complex and potentially hazardous environment, and effective management is crucial for safety and efficiency.
Now let's get practical. The syllabus takes us into the world of basic workshop practice and advanced practical training on marine machinery. This is where aspiring engineers get their hands dirty, learning to use hand tools, machine tools, and precision measuring instruments.
This is where theory meets practice, where they develop the fundamental skills they'll need to maintain and repair shipboard machinery.
It's all about building that mechanical aptitude, getting a feel for the tools and materials they'll be working with.
Exactly. They learn to use hand tools with precision, operate machine tools like lathes and milling machines, and use a variety of measuring instruments to ensure accuracy in their work. Tasks like creating square threads or fitting tongue and groove joints might seem basic, but they build a solid foundation of practical skills.
The syllabus also mentions welding shop activities, covering arc welding, gas welding, brazing, annealing, and the crucial skill of repairing leaky pipes. These are skills that can be absolutely vital at sea.
Imagine a leaky pipe in a critical system. Being able to quickly and effectively repair that leak can be the difference between a minor inconvenience and a major disaster.
So these are essential life skills for a marine engineer.
Absolutely. They learn different welding techniques, how to braze metals together, how to anneal metal to relieve stress, and how to tackle those pesky pipe leaks that are bound to occur on any ship.
Then we delve into the maintenance and repair of a vast array of shipboard auxiliary machinery. Auxiliary engines, pumps, filters, purifiers, freshwater generators, heating exchangers, air compressors, incinerators, oily water separators, and refrigeration plants. It's a daunting list.
It is, but it reflects the self-sufficient nature of a ship. They need to be able to maintain and repair all these systems that support the main engine and provide essential services for the vessel and the crew.
So it's like being the maintenance crew for a small, self-contained city.
Exactly. They need to understand how each system works, how to troubleshoot problems, and how to keep everything running smoothly.
The syllabus then goes into considerable detail on main engine and auxiliary engine maintenance, covering everything from identifying components to specific tasks like fuel injection pump maintenance, valve tappet setting, temporary pipe repairs, starting air distributor maintenance, cylinder heads overhauls, piston and conrod work, cylinder lubricator maintenance, crankshaft deflection checks, and even turbocharger maintenance. It's a deep dive into the very heart of the machinery.
This is where their training gets really specific, where they learn the intricacies of maintaining these complex machines. They need to know how to check crankshaft deflection, which can indicate potential alignment issues. They need to understand how to maintain fuel injection pumps and valves for efficient and reliable engine operation. And they need to know how to overhaul a cylinder head, a major undertaking that involves dismantling, inspecting, and rebuilding a critical part of the engine.
It sounds like a surgeon operating on a giant mechanical heart.
It's a good analogy. These are highly skilled tasks that require precision, attention to detail, and a deep understanding of the machinery.
And finally, in this section, we have boiler and steam machinery maintenance. While steam systems are perhaps less common on modern merchant ships, they're still vital in some applications.
That's right. While diesel engines dominate the scene, steam turbines are still found on some vessel types, like LNG carriers, often used for driving cargo pumps or for power generation. And boilers are essential for various heating and process requirements.
So marine engineers need to be familiar with both diesel and steam systems.
They do, and this part of the syllabus covers the identification of boiler components, understanding boiler mountings, turbines, combustion equipment, and steam traps. They need to know how to maintain these systems, just like they know how to maintain diesel engines.
All right, moving on to marine electricity, electronics, automation and controls, and high-voltage installations. This section covers the electrical side of things, which is becoming increasingly important in modern shipping.
Ships are becoming more and more reliant on electricity for everything from propulsion to automation. It's a complex and ever-evolving field.
The syllabus starts with the basics, the proper use of electrical measuring and testing equipment, like the Megger, clamp meter, and multimeter. These are the fundamental tools for any electrician, right?
Absolutely. Marine engineers need to be proficient in using these instruments safely and accurately to diagnose electrical faults, measure voltage, current, and resistance, and ensure the integrity of electrical circuits throughout the ship.
The syllabus then covers marine power generation and distribution, including AC and DC systems, alternators, automatic voltage regulators, AVRs, paralleling of generators, switchboards, and motor starters. It's like managing a miniature power grid on a moving platform.
It is, and it requires a deep understanding of electrical principles and systems. They learn about how alternators generate the ship's power, how AVRs ensure a stable voltage supply, how multiple generators are synchronized and connected in parallel to meet varying power demands, and how switchboards distribute the power to various circuits.
And what about those motor starters?
Motor starters are essential for controlling the large electric motors that drive various pieces of machinery on board, like pumps, winches, and fans. They provide a controlled startup and protect the motors from overload and damage.
The syllabus also mentions lighting systems, alarm systems, and various electronic instruments. It's a vast network of interconnected systems that keep the ship running and the crew safe.
These are all critical systems that depend on reliable electrical power and electronic controls. We're talking about everything from lighting for safety and operations to sophisticated alarm systems that alert the crew to potential hazards like fire or flooding. Electronic instruments are used for monitoring critical parameters like engine temperatures, pressures, and fuel levels. It's all about automation and control, making the ship safer and more efficient to operate.
The syllabus then delves into the fundamental building blocks of electronics: semiconductors, diodes, transistors, amplifiers, thyristors, and the principles of PID control. This is getting into the nitty-gritty of how all these electronic systems actually work.
Understanding these basic components is essential for troubleshooting and repairing electronic equipment. Semiconductors are the foundation of modern electronics. Diodes allow current to flow in one direction, transistors act as switches or amplifiers, and thyristors are used for high-power electronic switching.
And PID control, what's that all about?
PID control is a widely used feedback control loop mechanism that automatically adjusts processes, like maintaining a specific temperature or pressure, to a desired set point. Think of it like the cruise control in your car, constantly making adjustments to maintain the set speed. It's a fundamental concept in automation and control systems.
Maintenance and repair are, as always, crucial. The syllabus covers storage batteries, the detection of malfunctions, and troubleshooting electrical and electronic control equipment. It's all about keeping these complex systems running smoothly.
The electrical and electronic systems require regular maintenance to ensure their reliability. Trainees learn about the care and maintenance of storage batteries, systematic methods for identifying and locating electrical and electronic faults, and techniques for troubleshooting and repairing a wide range of control and monitoring equipment, from simple circuits to more complex automated systems.
And finally, this section specifically addresses high-voltage installations, which are becoming increasingly common on ships. This includes safety procedures, potential hazards, required PPE, lockout-takeout procedures, safety documentation, the construction and maintenance of high-voltage circuit breakers, insulation resistance tests, and the operation of high-voltage generators and motors.
High-voltage systems present unique challenges and risks, and safety is paramount. They learn about specialized PPE, the critical importance of lockout-takeout procedures to completely isolate equipment before work begins, the necessary safety documentation, the specific maintenance requirements for high-voltage circuit breakers, and the safe operation of high-voltage generators and motors.
It's a specialized area with a strong emphasis on safety, as the consequences of a mistake can be severe.
Absolutely. High-voltage systems are not to be trifled with, and proper training and procedures are essential for preventing accidents.
All right, shifting gears now to ship safety and environment protection and marine pollution awareness. This is a crucial aspect of modern shipping as the industry strives to minimize its impact on the environment and operate safely.
Environmental responsibility and safety are paramount in today's maritime world. It's not just about getting the cargo from point A to point B. It's about doing it in a way that minimizes risk and protects the environment.
The syllabus starts with MARPOL, the International Convention for the Prevention of Pollution from Ships. It covers the history, development, and 6 annexes of this comprehensive international framework.
MARPOL is the cornerstone of international efforts to prevent marine pollution from ships. It sets the standards for minimizing pollution from operational discharges and accidental spills of a wide range of harmful substances, including oil, chemicals, sewage, garbage, and air pollutants.
So it's a comprehensive set of regulations that covers all aspects of pollution prevention.
It is, and it's constantly evolving as new threats emerge and technology advances.
The syllabus then delves into specific measures for pollution prevention from machinery and cargo spaces, covering equipment like oily water separators, OWS, oil discharge monitoring and control systems, sludge tanks, slop tanks, and the oil record book, ORB.
These are all essential tools and procedures for preventing oil pollution. OWS and ODMCS are used to treat bilge water, separating any oil before discharge is permitted under strict limits. Sludge tanks collect oily residues from fuel and lubricating oil purification, while slop tanks are used to handle oily mixtures from cargo operations on tankers. And the oil record book is a legal document that meticulously records all oil transfers and discharges, providing a crucial audit trail.
So it's a multi-layered approach to preventing oil from entering the marine environment.
It is, and it requires constant vigilance and adherence to strict procedures.
The syllabus also covers regulations surrounding sewage, garbage, and air emissions, including controls on